Okay. Above we talked about ARP. Perform ARP requests. On the same network segment, you can directly request the destination. For example, PC1 and PC2 are the same segment. All are 1.1.1.0 network segment. You can directly request. The ARP cache table is cached locally for the current data. If every data communication, an ARP must be sent before communication. This is not optimal. Now on the internet, the number of messages sent is actually a lot. For example, I now have a relatively large message. Maybe a few G. If I watch a movie, then it is necessary to continuously send messages. Each packet actually has a specified size. That is, the message will not be particularly large. For each data packet, it has a prescribed value. We call it the MTU value of the link. I told you this before. For data, data is being sent continuously, sending from source to destination. Many messages may be sent at the same time. Keep sending. Then if every packet sent, data encapsulation. That means, for this purpose MAC is to be used frequently. If now every time before sending a packet, make an ARP request. It's not optimized. Very troublesome. So now, we designed an ARP cache table. Exist locally. You often have to send data. This ARP cache table will always be refreshed. Otherwise it may be aged out. Because it is a dynamically learned representation. This is enough for everyone to understand. So let me give you a summary of the process I just talked about. If the PC now communicates with the peer, it will compare. Is the IP address of the peer end suitable for you to be on the same network segment? The way to compare is your own mask and your own IP count as your own network segment. The other party's IP and its own mask are counted as the other party's network segment. Please pay attention. What we just said. They work out the same. They go through. But it's not work out the same. This will involve ARP. Now the data is the same. Data from the same network segment. As it can be sent. And be able to reply to it. Then before sending the data, it needs to investigate the other party's ARP first. That is to say, use ARP to investigate the MAC address of the other party. Before actual communication, it will detect the mask of the peer. Are you in the same network segment as yourself? If the two are considered to be in the same network segment now, then it borrows the ARP to achieve overall operation. That is, borrow ARP to capture MAC address. Only after that can the MAC be packaged. Then proceed to the next step. Implement this operation. Then send an ARP request. The other party will reply with an ARP response. This is the query we're talking about. But actually, before we borrowed ARP to achieve MAC address capture, first, check the local ARP cache. Everyone should know this. Certainly, ARP must be sent the first time. But the follow-up will first look at the ARP cache. Wait a minute to show you. In the current cache, if there is a corresponding relationship between the corresponding IP and MAC address, now you can directly encapsulate the data. If there is no local cache, then ARP will be used to capture the address. Let's take a look together. Still PC1 and PC2. Let's look here first. I make a mark here. Everyone will find. There will be no more packets. Let's ping now. Here it reappears a set of ARP. The content is the same as above. It's all a request. Then a reply. But for the following. Now. The 5 packet encapsulations have been completed. That is, we pinged. Ping back. ARP is back again. ARP is now aged out. So let's do a new test now. Watch carefully. I'm still here to make a mark. Now if I take PC1 to ping PC2 again. This yellow ARP will no longer appear here. Only pink messages will appear. I only send ARP now that there is no local cache. Then after sending, there is a local cache. Save the 005079666680 corresponding to 1.2. I won't post it now. Let's test it. Ping 1.1.1.2. Okay. We captured new data. But in this data, it seems that it really does not have this group of ARP packets. This is the markup I just made. The only thing left is the message of the ping command just sent. There is no ARP. Actually, when it is packaged, I have found that there is a MAC corresponding to 1.2 in my cache. So it directly encapsulates. If the lookup table does not, it will do this. Next, let's talk about some slightly more difficult. For the gateway, if it is the same network segment, then communicate directly. If there is no local, just request the MAC of the corresponding destination IP. But let's think about a question. What if it is across network segments? ARP message is a broadcast message. It is delivered within a broadcast domain. The second floor is all F. But for routers, each interface is a broadcast domain. That is, if the future PC wants to send from 192.168.1.100 to 192.168.2.100, that's actually going to the opposite end. May I ask how to package the MAC for this purpose now? ARP is now a broadcast packet. But each interface of the router is a broadcast domain. This is the range to which broadcast packets are delivered. That is, if PC1 sends an ARP request now, only this interface of the router can be reached at most. It won't be forwarded here. This device cannot receive the request from the device on the left. Then it will naturally not reply. Logically speaking, if it doesn't reply, there is no way to encapsulate the second layer. If now they are data forwarding across network segments, then the second layer will encapsulate the MAC address of the gateway. PC performs calculations locally. Compare whether they are on the same network segment. It finds that it is not in the same network segment as the peer device. So now when it is sending ARP packets, no request to the peer device. Instead, request the MAC of the IP address of the gateway. That's what we just said. The target IP in the message will become 1.254. Target MAC is the MAC that requests the interface of the gateway. Because for PC access across network segments, it will go to the gateway. This is its gateway. Then since the PC now knows it is not in the same network segment as the peer device, as long as there is now a gateway is configured on the PC. It goes to the gateway. It will not find the address of the peer device. It will directly request the MAC of the gateway. The gateway will respond accordingly. So if the data crosses network segments, actually, the data will go to the gateway. It's here to help you forward. The same goes for the return packet. If the PC is now accessing across network segments, it goes to request the MAC of the gateway. When it requests in local ARP cache, the MAC corresponding to the IP of the gateway will also be cached, forwarding across network segments in the future. I will directly encapsulate the MAC of the gateway, forwarded as the destination MAC. That is, when the PC is accessing across network segments, the broadcast gateway will give it a unicast reply. For cross-network communication, it directly finds the gateway. When communicating on the same network segment, it will directly find the peer device. So everyone should know the importance of the gateway by now. Now you may not have a good understanding of the gateway. Later when we start talking about routing, gradually everyone will have a deeper understanding of it. ARP request for cross-network communication. Gateway. ARP request for communication on the same network segment. The question is directly on the other party's device, because it is the same network segment, so it can be directly accessed by ARP broadcast. The other party can reply, because it involves a data encapsulation problem. So ARP is very critical. In fact, we sometimes refer to ARP. There is another thing. Gratuitous ARP. It has another name. Gratuitous ARP. Let me show you. For example, this is PC1 and PC2. Let me modify the IP address of PC1 just now. Change it to 1.1.1.3. 24-bit mask. Let's make another mark here in the message. Wait for it to send a new message from below. Let's take a look. I am making a modification now. You see I didn't ping. Just change the address. The following packets are captured. It will also send data packets if the address is changed. Send 3 gratuitous ARP packets. This report also has some characteristics. Let's move it up. We open this message. The characteristic of this message is that when it is in 3-layer encapsulation, it is also an ARP. But it's just that this ARP is special. Its sender IP is itself. Target IP is also itself. Equivalent to. It configures an IP address for the interface. This interface only needs to be configured with IP by default. We'll send out packets. Make an ARP request. Request is. The destination IP is the same as the MAC address of the device. Now this is 1.1.1.3. The reason why we still have to request 1.1.1.3 is to do a duplicate address detection. This is what it does. The role of gratuitous ARP is duplicate address detection. I ask you a question. If the PC sends a data packet now, destination IP is itself. Target IP is also itself. Now the peer has received. For example, PC1 sends a data packet to PC2. PC1 is configured with an address of 1.1.1.1. PC2 is also 1.1.1.1. After PC1 is configured, outbound packets PC2 received need to reply to PC1. In the same way, for the current device, it received an ARP request, should give a reply. We just configured 1.1.1.3. So it will reply 1.1.1.3. So in theory, if in an environment, if your configured IP address conflicts, then you will receive a reply from a person with exactly the same name as yours. If you don't get a response like this, it means you have no conflict. So, it is used for duplicate address detection. So how does it work? After an interface is assigned an IP address, gratuitous ARP. So whether we configure it manually or automatically issued IP, it will also send. You will learn DHCP later. Dynamic Host Configuration Protocol. In the whole environment, this IP is unique, because as long as there is no conflict, no device will reply you. If there is a device to reply you, just to prove it's the same as your name, you need to change your name. When data forwarding is performed as a whole, it is not acceptable for two devices to have the same name. Let's move on to the next question. This problem is a little more complicated. Let's add a few devices now. Add a router. Then add two PCs. What we want to do is an extension function in ARP. Proxy ARP. We first make a connection to them. Relatively speaking, it starts up pretty fast. Let's refresh it to open it. We also turn on the device. After opening, we are going to make a configuration. Then, before configuring, first of all, we need to plan the addresses for them. I took it to the drawing board. We plan the address. What we do today is not cross-broadband. We are doing the same network segment. Suppose the IP address of the PC on the left is 192.168.1.100. Sometimes you may find you forgot some configuration. For example, if you forgot to configure the gateway. Suppose the IP address of the PC on the right is 192.168.0.100. 23-bit mask. Actually, for ARP proxy, when you refer to static routing in the future, point out the interface. It will also have some relationship with. Only, nobody uses that thing like that anymore. For now, it is not very common that the host does not have a gateway. Although this feature is very useful, can solve the corresponding problems. But in fact, we are now configured to do. I hardly ever use this feature much. Let's take a look at what it can do. On the left is 192.168.1.100. On the right is 192.168.0.100. Let's also configure the interface on the right. Suppose the interface on the right side of the router is 192.168.0.254. The interface on the left is 192.168.1.254. They are both 24-bit masks. This is the respective gateway representing the PC. But we don't configure the gateway for a few days. If we access across network segments, in fact, the gateway is to be configured. Let's configure them. First, think about a question. For this scene, are the two PCs on the same network segment? PC2 is 192.168.1.100. 23-bit mask. PC3 is 192.168.0.100. 23-bit mask. Now for PC2. 192.168.1.100. The mask is 23 bits. The network bit representing it is 23 bits. The last 9 bits are host bits. Then whether it is 1 or 0. Both are 24th. They are both on the same network segment. I forgot to write a space here. Reconfigure 192.168.0.100. Okay. The two of them are actually on the same network segment. All in the 192.168.0.0 network segment. Then we configure the network segment. You can check it out here on PC2. Now I have not configured a gateway for it. That is, now gateway is empty here. I only configured an IP address and mask. Gateway not configured. Gateway is empty. Then for PC3, I did not configure the gateway. This means that if data access across network segments, I can't access. So now we go into the router. Enter this interface. We configure it accordingly. This will be slightly slower. We enter configuration mode. Then enter the interface. The one on the left is the 00 interface. We configure an IP address. It is 192.168.1.254. Then we configure the mask. 3, 255 and 10. Because it is a 24-bit mask. Followed by no shutdown. Enter the 01 interface. We also configure an IP address for it. It is 192.168.0.254. The mask is also 3, 255 and 10. We also give it no shutdown. It is now configured. Let's walk through the process. As a PC, let's see what it should do now. Before that, we still have to capture packets. But I turned off other environments before. Because this is the previous configuration. When we captured on the left and right interfaces of R1. First look at the 0 interface on the left. After that, it is also opened here on interface 1. That is, we now capture one interface. Open both. After we open it, let's go on. For the current experimental environment, let's think about the process. First ask everyone. If the left PC pings the right PC, can you ping through? What we say now. This is the 0.0 network segment. This is also the 0.0 network segment. Both are on the same network segment. If the PC now judges that the other party is on the same network segment as itself, it should send ARP broadcast directly to the other party. Query the other party's MAC. For example, before the PC wants to ping each other. To encapsulate the second layer. I don't know the other party's MAC now. The PC must first send an ARP packet to ask MAC. But the embarrassing thing is, they are indeed on the same network segment. And for routers, the left interface is the 192.168.1.0 network segment. The right interface is the 192.168.0.0 network segment. The two interfaces of the router. Not in a network segment. But for PC. Overall. Can be on the same network segment. For PC1. They are on the same network segment. For PC2. They are on the same network segment. But for routers. These are two interfaces. Now you will find the overall network bit of the two PCs is too short, causing them to cover a larger range of network segments. But for routers, network bits are too small, causing them to have too narrow a segment range. You will find, in theory, they are both right. They are both in the same network segment. These two are in the same network segment. And for the router, these are two network segments. We don't talk about switches. A switch in the middle. This is the same as a missing switch. Both of them cannot be pinged. We just said, PC2 sends an ARP broadcast to ask. But unfortunately, ARP broadcasts can only be forwarded under one broadcast domain. For the interface of the router, each interface is a broadcast domain. That is, now this message can only send to this location at most. This ARP request cannot be sent to the other side. Let's test it first. It is now 192.168.1.100. Ping 192.168.0.100. Let's take a look. We can find out that it seems to work. In theory. It should be unreasonable. How come it works again now? That's another question. First of all, for the router. Let's first look at the left interface of the router. Everyone will find. Indeed received ARP packet. I stopped it. Don't worry about the other ones what they are. What is asked in this ARP packet is, who has 192.168.0.100? Call 192.168.1.100. 1.100 is the PC on the left. 0.100 is the PC on the right. I cut this picture. Look at. Because we follow the message. To analyze it will be more accurate. Let's look at this picture. Now PC3 is 0.100. PC2 is asking PC3. Then now you will find. The device got a reply. There is now an ARP. This is called ARP request. Is a request message. The following is called ARP reply. Is a reply. Now it receives a response. And it got the MAC address of 0.100. That is. It gets the MAC of the right PC. Let's take a look. Is this MAC the MAC of the PC on the right? We go into this PC3. Check its MAC address. We will find. This is not the MAC address of PC3. PC3 is 005079666803. It now replies with AABBCC001000. It's not a PC3 MAC. In the process, it goes to request PC3. But PC3 did not reply to PC2. But it does get a MAC address like PC3. So whose MAC address is it? It must be real. Now the left PC is requesting the MAC of the right PC. It did get a reply. Now the MAC corresponding to the PC on the right is AABBCC. But we looked at the device's MAC. Found that it is not the MAC address. So, whose MAC address is this AABBCC? Okay. Is the 00 interface of the router. In fact, we don't have any other interface now. A total of 4 addresses. Both of them ruled out. Now there are only 2 of them left. It feels like this address. Because the MAC address works on a link. So is the address of this interface. So it replies pretending to be PC3. Let's check the current interface of the router. We have to get out first. For example, I am now checking a layer 2 interface. I'm going to see Ethernet. It is the 00 interface. Let's see what's written here. Address is AABBCC001000. This looks familiar. This is the 0 bar 0 interface on R1. It's a MAC address. This is what we are answering now. AABBCC. That is. The router uses its own interface to impersonate the address of PC3. Reply a MAC address to PC2. The proxy function of ARP we talked about today. It is enabled by default on Cisco devices. So when the PC sends, it is able to help forward by default. Okay. We just looked at the message on the left. Let's now look at the message on the right. That is the interface on the right. I pause. Start here. A message is now sent. PC3 is 192.128.0.100. Tell 192.168.0.254. So it is. Who has PC3? Right interface of tell router. Because this is the packet captured under this interface. It is equivalent to another ARP request now. Is sent through this interface. Then the corresponding PC3 replied to it. 192.168.0.100. is at 005079666803. Here is the real MAC address of PC3. The device on the left asks the router. The router replies with an interface of its own. Then the router asks the device on the right. The device on the right puts the real MAC. Told the router. When the final forwarding. The device on the left sends data to the router. The router helps forward the device on the left encapsulates the MAC of the router. The router encapsulates the MAC of the device on the right. The PC now interacts with the left and right interfaces of the router. This is an interactive process between them. Then we make a simple summary. Let's continue to look at this picture. For routers. Proxy for ARP on Cisco devices. The interface is to enable the proxy function of ARP by default. Then when PC2 sends a request to the left interface of the router, it requests a MAC address of 0.100. When the device receives an ARP request, if the target IP it requests is not it simply drops the packet. But now the router will not drop the packet directly. As long as the ARP proxy is enabled on this interface, it will not directly drop the packet. It will look at who the message is looking for to ask for the MAC address. It is now looking for 0.100 to ask for the MAC address. Then it checks to see if there is any. If so, it will reply to it. But if not, it will activate its own ARP proxy function to help the equipment. Certainly. It's also not the actual PC that replied. It also responds to this interface. Otherwise retweet. There is no way for you to package the MAC. In the next paragraph, the reply is also this interface. It's just that it involves the question of asking again. Not everything. The router itself has to be able to. I give an example. Suppose you have a question you can't do now. You think I will do. So you need to find a good person to ask. But you don't actually know where this guy is. You send this data packet. Can't even get to this place. The data packet arrives at the router in the middle here. It doesn't know if it will do it. But this data packet arrives here. Logically speaking, the router is not the guy you're looking for. It won't know your question. It drops the packet. Then for the device. Since the device has proxy function enabled, it's like it's now helpful. If you now send a packet to it you have to ask it a question. This question it won't. But it can help you ask. Ask the person you want to ask. But the premise it asks is, it knows this person. It's the same in this picture. The data is now going from 1.100 to 0.100. Since PC2 is now requesting 0.100. Router is not 0.100. It will help PC2. Not directly discarded. It goes to help PC2 ask PC3's MAC. But only if it knows where the device is. That is, it has to be connected to PC3. It needs to have a route to PC3. If now a line connects the devices at both ends, an address is configured on the left. An address is configured on the right. The right side is called the direct route on the left side. A direct route will be generated on the router. Since we are now going to visit the network segment of 192.168.0.0, it is a direct route of PC2. So it can reach. It's okay if you don't understand here. Because many knowledge points in the course are coherent. So it is easy to encounter knowledge blind spots. When we talk next class, let's have a deeper understanding. Here is a direct route. There is also a routing table. There is this representation in the routing table. Prove that the router can reach. PC2 now sends a message to the router. It doesn't matter. Although this broadcast packet can't get through, the router can help PC2 send another broadcast packet to request. Because this broadcast packet can pass is due to the isolation of broadcast traffic by the hardware. This router can't help PC2. All it can do is help send another packet. Help to ask. This is what we call ARP proxy. It will help to send another ARP. Then when this ARP is sent, just use your own MAC address as the source. I went to PC3 for the address. Later, form an ARP cache locally. But although there is a local cache, but it won't cache this to PC2's. That is, PC2 is requesting a MAC of 0.100, while the R1 has gotten its MAC. It also doesn't tell PC2's if the left device. It is really packaged by the MAC of the device on the right. PC2 is under this broadcast domain. Can't reach PC3. What we call encapsulation based on MAC address. It is performed under a broadcast domain. It is a concept on the link. PC2 cannot find the peer device, so it can only find the router in the middle first. Let it do a retweet. All data encapsulation required. The router will have an ARP cache. ARP cache it corresponds to. It is a correspondence between an IP address and a MAC address. Then everyone has to think about the corresponding relationship. As long as a device wants to send data. Data encapsulation. Just perform data encapsulation. IP address and MAC address must be encapsulated. Then as long as you need to encapsulate, then there is ARP cache. So the ARP cache is present on all devices that will communicate over the network. Whether PC, router, firewall, switch, all have ARP cache. Certainly, the switch has to be a layer 3 switch. Otherwise, you don't even know what an IP address is. There will be no correspondence between IP and MAC. Let's take a look. First, the two PCs can be pinged. This is what we have verified. We can do a verification on R1. Let me check. ARP on my device now. Okay. Everyone can see. For me now, I have a corresponding ARP on my device. And the information I got is correct. In addition to the interface on its own body. It does not count. This is 0.100 for MAC. This is 1.100 for MAC. The one on the left is 050079666803. The one on the right is 005079666802. We can also take a look here. 005079666802. This is the left PC. Let's check ARP on PC1. Everyone will find. Here there is 192.168.1.0. That is the ARP of the right PC. This is what we just demonstrated by capturing packets. The left PC thinks. Now the address of 0.100 is AABBCC. Data encapsulation. It is encapsulated like this. For PC2. It does not know that. The router has opened a proxy function to help itself. It thinks they are on the same network segment. PC3 reply is the same. It thinks they are on the same network segment. PC is unaware. Middleware help is a function that it enables. The PCs at both ends regard it as a mutual access on the same network segment. To us, it also doesn't have to be a physical direct connection. It's not necessarily connected by a single thread. It may also be connected through a switch. Anyway, a network segment is directly connected. As for passing through the router in the middle, they don't know. Okay. Next we will talk about another content called ICMP. Control Message Protocol. This is an important protocol at the network layer. But it is not actually encapsulated at the network layer. Now the network layer uses. More is the encapsulation of IPv4. 2-layer encapsulation. 3-layer packaging. Logically speaking, it should be a 4-layer package. But ICMP is the same as ARP. The top layer is ICMP. There is no transport layer and application layer behind. Is encapsulated on top of the IP header. This is 3 floors. This is the second floor. This is ICMP. So we often call ICMP a layer 3.5 protocol. Because it works on top of the overall 3 layers. It is encapsulated in this location. The back is the same as ARP. Nothing at all. It is also a special message form. Then the ICMP we talked about today. What exactly does it do? When we transfer data in the future, the first thing to know is that for the ICMP message, the transmission of data pays attention to the back and forth of data. Let me explain what this means. The host sends a message to the peer. The peer needs to reply with a message. This is what we said. Data goes back and forth. Represents that the 2 hosts are connected. There is no error in passing between them. So now this message. Able to reach each other. And the other party also allows to return data packets to host A. Then once host A receives the data packet from the other party, it knows that it is now connected to the peer. Before the host wants to send a message to the other party, first ping them to see if they are connected. If you pass, send it later. It's like in real life when you're talking to someone. You call him first. He promised. You continue the conversation. If you are far apart, or separated by several people, you suddenly start talking to him. He wasn't there when you spoke. Or you call him. It didn't hear either. So ignore you. Then you won't keep talking. You have to make sure he is listening to you. And he can hear what you say. There is no problem. You can transfer again. It is used for error detection. It comes in 2 forms. One is ping. One is traceroute. Let's start with this bug report. ICMP has 2 forms. The ping we have learned so far is one of ICMP. And traceroute is also a. So let's talk about this ping first. Sometimes when we go to ping an address, you will find I am within a certain period of time. No response from the other party. This is one of the forms. We call it request timeout. Let me show you. For example, I'm going to ping an address now. 2.2.2.2. It's definitely not working. So it will show request timed out. That is, if I go to ping an address, no reply from the other party within the unit time. Called request timeout. So what does this request timeout mean? Let me give you a brief explanation. For example, now this is PC1. This is PC2. Passed through a lot of equipment. Because in the end, it goes through many devices of the operator. A route that executes. Then in the process of forwarding. As long as this PC1 sends out the data packet, send to the next device. However, due to various reasons, resulted in no reply. This is called request timeout. So there are various reasons that may be a problem here. Or something is wrong here. Or here. Here. Including when the subsequent data packet is returned. There is a problem with any node. didn't go back to this device anyway, are called request timeouts. For host A, the request timed out. Then there is another situation. The second is called destination host unreachable. For example, I will ping another address. I'll check the current address first. Look at my network segment. I go to ping 192.168.1.222. Here is an unreachable destination host. If I perform the corresponding ping command, I get a response in my command line. Unreachable destination host. My order was not sent. Or was blocked. It has many possibilities. I give a simple example. Now this is PC1. This is the first router. Through many routers. Finally arrived at an address on the far end. If now, my message is going to the first router. When doing the first retweet, there is a problem. Here it will show that the target host cannot be accessed, because the data cannot reach the next device. Devices are sentient. It knows this is not sent out. This is called host unreachable. Usually, there are two kinds of. The first is that PC1 did not send data. For example, it has no appearance of ARP. No way to encapsulate. Suppose it is going to visit this 1.222. But actually, this network does not have this 1.22. It is equivalent to not having this host at all. Can't request its MAC. There is no way to encapsulate. So there is no way to send. It means that the data has not been sent out. The second is, we may do a data interception on the router side. That is, this data needs to access an address on the back end. But I'm cutting the flow here. No access. So this data packet cannot be sent out. Then here will prompt. Unable to reach destination host. Here's what the two error messages suggest. Everyone should know this. Okay. Let's move on. This is the format of an ICMP packet. I'll show you. This is a two-layer encapsulation. This is the E2 I wrote for you. Three-layer encapsulation IP header is packaged at this location. In addition to the verification of the second layer. The follow-up. There is no fourth floor. Only one ICMP. There are types in it. Code. Checksum. ICMP is specifically a content. Well, actually for us. Different messages represent different content. Here are its specific details. Then let's take a look at type and code. Generally speaking, encapsulation based on IP header. We call it encapsulation based on 3 layers. ARP is above the second layer. This is the second floor. The 2-layer package is E2. We are called encapsulation based on the second layer. Working on the second layer is called encapsulation based on the second layer. This is a layer 2.5 protocol. ICMP is encapsulation after the second and third layers. We call encapsulation based on the network layer. Also known as working above the network layer. Is a layer 3.5 protocol. But strictly speaking, it does not belong to the transport layer. If you have to ask which floor it belongs to in the second, third, and fourth floors, it belongs to 3 layers. Because there is a port after the transport layer, we are going to control. It cannot provide the port of layer 4. So it definitely doesn't belong to the 4th floor. It can only be said that it is a 3-story. Because it cannot realize the functions of the 4 layers. Let's briefly talk about these unreachable. Host unreachable. Network unreachable. Actually these two. I just told you. The internet is not all smooth sailing. Suppose my data is sent. This is the sender. This is the destination. This data. To the next device. Then whatever the reason behind. As a result, this data cannot be returned. This is called network unreachable. The host is unreachable. The device may now be doing some kind of policy. It doesn't let others ping it. Or, I may have sent the data now. Since the destination host may not be online. Also known as host unreachable. Or, I am now going to ping this address. Doesn't exist at all. Then I can't do data encapsulation. This is also known as host unreachable. Let's focus on these two. Protocol unreachable. Port unreachable. Because I didn't explain these two. Agreement unreachable means that when I send a data now, the destination has been reached from the local. Then I will now communicate accordingly. Based on the network layer. Up there are different agreements. For example, TCP and UDP at the transport layer. If what I want to access now is the TCP protocol. But now the other party has not opened this agreement. So now I have no way to allow the other party to access. That is, my protocol accesses the other party's protocol. If the other party does not open this agreement now, I will reply a message to the other party. Protocol unreachable. But usually, these unreachable packets cannot be received. Because now for many devices, by default, the error message reply of ICMP will be turned off. But, in case the network goes down one day, according to these error codes you can, to do a corresponding investigation. Port at the top. I can access the TCP protocol now. Suppose I now access the other party's port 80. For example, my local port is 1027. A local port greater than 1024. Random access to port 80 of the other party. The TCP protocol of the other party is indeed open. But the HTTP web service is not open. Port unreachable. So from network to host. To agreement. To port. Layer by layer. Is more and more detailed. But usually, UDP and TCP protocols are unreachable and very difficult to catch. Because for these public agreements, it is installed on the default network card. Generally, it is not easy to close. So I can't catch this thing. In addition, we will disable replying to this error message. What does it mean? Let me give you an example. This is a PC. There is a router on the public network in the middle. Assume that this is the peer router that the PC wants to access. Connect with each other. Now it is hoped that from the sender to access the peer. Generally speaking, there will be some corresponding strategies here. That is to protect. For example, the address of this server is 2.2.2.2. This address is 1.1.1.1. But in fact, now the server is not using the public network address. Private network. The export here is the server for NAT. The public network is also used internally. Now go to ping 2.2.2.2 from 1.1.1.1. For data. This device has routing. Data can come. But this device is not allowed to access. Logically speaking, it is to reply host unreachable. Or depending on the situation, may reply network unreachable. Can't access this device right now. Policies may have been made on this device. A call may be performed under the interface. When the data packet arrives here, it is intercepted. In theory, the router is obliged to reply with an unreachable message. But please be careful. If message reply, we are going to encapsulate the source IP of the third layer. The default encapsulation is the IP address of the outgoing interface. Now this interface replies to the PC with an unreachable. That is equivalent to exposing the interface IP as some more private servers. Now you know the IP address of the uplink device exit. Usually, I don't want this address to be revealed. So even if I do the strategy here, after the data arrives, it fails. Will not reply to unreachable messages. If the device replies with an unreachable message, will come out with IP. It is equivalent to leaking the IP of the current interface. Generally speaking, we will not reply packets to it. Everyone in future work. You can test devices from many manufacturers. Even if ICMP is unreachable for various reasons, you also don't get unreachable messages. It will not receive ICMP packets. There is a code value inside. Look at this type code, corresponding to this type and encoding. In theory, you will receive an ICMP message. But in many cases you can't receive. That is to say, whether the request timed out or was unreachable. It's not that you just have a network failure. The other party will definitely give you a reply packet. Depends on the other party. Is the service of replying data packets to you enabled? So there is no absolute. In many scenarios for safety, may not be able to reply. If this feature is enabled, can reply. Next, let's talk about the application of ICMP. ICMP has two major applications. The first one is ping. For ping, actually, every time you send a ping, it sends an ICMP packet. Under normal conditions, you ping the peer on the device. Will send 5 packets at a time. If I go to ping now, suppose the address on the right is this. The default is 5 packets. Then in these common parameters, only 2 are commonly used. One is called repeat. One is called source. Let's talk about this repeat first. Repeat means, how many do you want to send now? How many times do you want to ping? Let me demonstrate. For this router, I first look at the interface of the device. I have now configured an interface address on the device. Then I'll ping myself. Suppose I ping 192.168.1.254. It's sure to work. Let's see now. All we can see are 5 exclamation marks. That is, sending 5 is written here. Sent 5. Then you can specify it here. For example, I specify repeat here. Specify it only sends 1. If I give it 100, it sends 100. If we want it to ping all the time, let's say I let it ping 10,000. We will send 10,000. Press the Control key plus the number 6 key to terminate it. Otherwise it keeps pinging until 10,000. If you want to ping an address under Windows, how to ping it? For example, I'm pinging Google right now. Just enter A to ping it all the time. Let's look down. Have a source. I draw a picture to explain. When we talk about experiments in the future, we'll talk about the loopback interface, called loopback. When we do experiments and work on projects in the future, the source command is often used. A device on the left. A device on the right. Now the devices need to ping each other. There is a direct address between the two of them. Like how much? The one on the left is 1.1.1.1. The one on the right is 1.1.1.2. Because they are directly connected. So you can directly. But if on the left side this device here, loopback. For example, this loopback address is 2.2.2.2. The device on the left can directly ping 1.1.1.2 because it defaults to this outgoing interface to send messages. If the reply packet, the destination IP, is the left device, the device on the right also knows how to get to the device on the left. The two of them can pass. That is, if no source is specified, it is the outbound interface. If source is specified, equivalent to now, it is from the address 2.2.2.2 of the left device. Go to the right device. Data can pass. Because when the data is sent, check the route on this device. But when replying to the packet, for the device on the right, it is not replying to 1.1. 1.1. It is replying to 2.2.2.2. It does not have the address of 2.2. Then it can't come back. Where are loopback addresses often used? Used to simulate a network segment behind this device. One of my devices on this device returns configured at 2.2.2.2. It is equivalent to connecting a device behind this device. This device is 2.2.2.2. Here is 2.2.2.1. I'm on this device with 2.2.2.2 as source to ping this 1.1.1.2. Now the two network segments can communicate. That is, you can go directly to ping 1.1.1.2 now. You use 2.2.2.2 as source. It may not be possible to ping 1.1.1.2. If it doesn't have a route, it won't work. When we go to learn routing later, often originates from an address to ping another address to ensure that the routing configuration is correct. Less likely to be involved in NA. In NP, you will often come into contact with. Let's move on to the last thing. Traceroute. This can see what happened to the equipment along the way. There is also a source in traceroute that can be specified. There is nothing special to pay attention to. I will give you a simple demonstration. Still take PC as an example. I will give it a trace route first. Add a dir. Don't worry about this. I don't want it to go to domain name resolution. For example, I give it 4114. Let's test it. It is the same as ping. They are all encapsulated with ICMP packets. But you will find there are many symbols in the middle. We wait patiently. Usually use this command. You will find some places can go. Can't reach some places. That is to say, I will go to such an address in the future. Public network addresses along the way. We all know. The domain name resolution server is actually a public network service. I have now visited an address. This is a public address. Along the way, you have to go through a lot of devices. On the public network are public addresses. What I want to know is my PC accesses to the public network. Another time when the service was finally docked. Who are these devices in the middle? We will use traceroute. Here you will find there are a lot of things we can't catch. Many are symbols. For the current overall equipment, it will have a security feature. We now talk about its mechanism as a whole. Why it can track so many devices. I give an example. I draw a corresponding environment. I am drawing 5 routers now. Device 1 is 2.2.2.2. Go to access device 5. Device 5 is 1.1.1.1. When I visit, how does traceroute retrieve each device? This is called traceroute. It is based on the TTL, and the entire IP packet is carried out. I said TTL when I talked about the message before. TTL is time to leave. Where does this message go? You can't forward it down. If a message is received now is 0. TTL value is 0. The packet will be discarded directly. Device 1 sends a message to 1.1.1.1. That is, from 2.2.2.2 to 1.1.1.1. First a message is sent. In this message, TTL is equal to 1. This proves that this message can be sent once below. Now after device 2 receives the message, the local will subtract 0 from this one. Becomes 0. Once this message becomes 0, it can no longer be sent down. It is equivalent to the termination of this message to device 2. Can't send it down anymore. So now device 2 will return a TTL timeout to the source. This means device 2 will use the address of this interface to reply to device 1. Device 1 receives the message and knows it is this interface. It knows who its next device interface is. Next we will send a new message. In the new message, TTL is equal to 2. The message is here. TTL minus 1 equal to 1. Can continue to send down. Post here. After receiving device 3. TTL minus 1 again. Minus 1. Reduced to 0. Once equal to 0 here. It proves that the data cannot be sent down. Now tell device 1. TTL timed out. The packet of device 1 did not arrive at 1.1.1.1. So device 3 will also use its interface. Send a message to device 1. Device 1 gets the address of device 3. Next, TTL is equal to 3. Arrived at device 4 here. Device 4 will now also reply with a packet to device 1. After device 1 gets the address of device 4. Then go on down to device 5. This is the destination. The message is also over. But device 5 will also reply to device 1. Device 1 knows that it has arrived. So it is equivalent to in this process. TTL keeps increasing. Cause the packet to arrive at a new device whenever. They all have to reply to device 1 with a timeout message. Then use this as a means. Get the IP address of each interface. So device 1 knows which device it has passed through. According to us, we should be able to get other equipment. Why do symbols exist? Because some equipment along the way is invisible. That is to say, a detection based on TTL value timeout may cause the address of the device to be exposed. That is, IP addresses of devices along the route will be exposed. Please pay attention. On our website, especially within operators, including possibly other public networks, many addresses that serve, it doesn't want you to know. Now you can see. It's all insignificant addresses. Those more important devices. And some important configuration addresses. You can't see. So these devices are forbidden to send ICMP-based TTL timeout packets. The TTL value is also one of the ICMP messages. Except that it uses the value different from what we just said. It is 11 and 0. You don't have to remember this. It is also the error message of ICMP reply. That for us. Some devices do not allow replies. You can't see it if it doesn't reply. But it will also help forward. Like the devices I just talked about. It can help forward along the way. That is, the PC has now sent a data post here. It doesn't reply to you. For example, TTL value is equal to 2. It doesn't reply. But send TTL value equal to 3. It helps you forward. Because you are now on the public internet. It is a public network device. You can't get its address. It can help you forward. But it doesn't message you back. Then what you see is the symbol. For example, this address allows you to reply. You can see. If you are not allowed to reply, what you see is the symbol, including some addresses you can't see. Okay. Some students will ask, what do these three symbols represent? It means that if the device sends 3 consecutive, if the TTL value is equal to 2, while other devices do not respond, then after sending 3 messages, the TTL value equal to 2 will no longer be sent all the time. It is time to send a TTL value equal to 3. Just skip it and move on. At last, ICMP has a problem with redirections. We just saw this in coding. That is, the message type. The TTL value timeout is also an ICMP message. It's just that it's 11. Here is 0. Here is an echo reply and echo request. When we send a ping, this ping packet is sent over. It's called echo request. The ping packet is sent back. It's called echo reply. Now let's talk about ICMP redirection. It is very simple. For us now, let's check the environment first. Host A's IP address is 10.0.0.1. Host A's gateway is 10.0.0.100. The internet is connected behind the gateway. If I want to go online in the future, my traffic goes like this. But you will find, now there is a server in the company. The server is 20.0.0.1. Host is 10.0.0.1. If the data is sent now, the host wants to access 20.0.0.1. Then in theory, the device is here. If people see it, the data should be transmitted like this, because the device is on the left. But for PC, it is on the 10.0.0.0.0 network segment. It is on the 20.0.0.0.0 network segment. If you access it across network segments, the host cannot directly find the server. Only gateway. But for the gateway, now the data is at the gateway. But the connection behind the gateway is the internet, dealing with the business of the operator. The internal server is here. Then the internet needs to help the server forward, because the server wants to access. The data has to be reset like this. That is to say, the data is transmitted like this. That actually, the data should go like this. It shouldn't come to the gateway. But since you configured a gateway, now across the network segment, gateway, so its contradiction appears. The gateway will now consider, if you visit now, better not to find the gateway, because the server is on the left side of the host. Just go to the left for the data. For the gateway, there will be a routing table. This routing table is premised. The routing table needs to know that the network segment 20 is passed in this way. To do a re-item, which is equivalent to, now the gateway discovers. After the data is passed, the gateway receives the message from the host through this interface. The gateway needs to help the host forward. You have to send the message through this interface again. For routers, if the future goes to the server, the next device to arrive should be here. Then the router will tell the host, if going to the address of 20.0.0.1, the next time the interface to this device is directly reached, the router sends a message to the host. Point out the direction of the host. But please note, just for such a destination IP to be accessed, to specify a direction. This is called ICMP redirection. That is, different network segments need to find a gateway. But the gateway Received a message from this interface. It wants to help forward. Have to switch out from this interface. And for the gateway. Look at this interface. Since the data can be transferred from here, then here, then it means that the router can go directly to this. Also in the same paragraph. And it happens that there is also a route to it. But please be careful. It is only for one destination like this. To tell you next time, go straight to the left. Then if your future, for example, you visit an address 8.8.8.8, such cross-segment access. Should you go through the gateway? Go through the gateway. This is how the data traffic goes normally. Only when you send a data. When it still comes out of this mouth, it will send you a redirect. Tell you now the next device is going to the left. That is to go through this interface. Redirect this message inside. It will point you to this destination in the future. Next device go this place. It will only go like this. When accessing the server. This is called ICMP redirection. Host and device are directly connected. It means that the interface of the router can directly send to the host. The host wants to forward to the next device. It must also be passed to the direct connection device. The three of them are still on the same network segment. So don't bother going astray. Just go straight away. This is the redirection. Okay. We'll stop here. Then we also hope that students can follow us. We are ThinkMo Education. I'm Grolin Annesley from ThinkMo. I hope today's content is helpful to you. See you next class. Bye classmates.